last time we were talking about distortionless transmission, meaning what are the properties that the system needs to possess so that if I put a signal in, I get the same signal back. And our standard view of a linear system is like this. We have a system with an impulse response h of t, associated frequency response h of f, and input signal x of t would produce the output signal y of t. Or I can say that if the Fourier transform of the input signal is x of f, Fourier transform of the output signal is y of f, and we have two relationships. Y of t is x of t convolved with h of t, and y of f is equal to h of f multiplying x of f. So this is what we, our view of the linear system. Above the lines is the time domain, below the lines is the frequency domain. We have a distortionless transmission when this happens. Y of t is equal to possibly some gain, G0, which is a constant multiplying, just a constant multiplier. I have capital in the notes, so let me put G0 here, times x of t, and we allow some potential delay, Td. We're saying that the signal is, that the delay in the transmission of the signal is not the distortion, right? Because we realize that nothing propagates it instantaneously, and there's some components that some delay that is picked up along the lines as the signal propagates through this linear system. We here present this in a view that this is a single box, right? In reality, what I'm talking about here is the whole system end-to-end. We can think of this as a, for example, communication system that I put in the signal here, it goes, gets digitized, quantized, transmitted, goes to satellite and back, and then comes on the other end. The question is, does the whole system behave as a distortionless, and what should be the property of the system overall so that the system is distortionless? This is the requirement, and as you can see, it is specified in the time domain. We can have an equivalent requirement in the frequency domain. If I take the Fourier transform of both sides of this equation, I get that y of f has to be equal to G0, and then the Fourier transform of the delayed signal is going to be x of f e to the minus j 2 pi f t d. Or I can understand this as G0 e to the minus j 2 pi f t d times x of f. I wrote this deliberately so that I can isolate these two components and call that an ideal transmission system. So what does the ideal transmission system have? It has to possess in terms of its properties. It needs to have a constant magnitude. I can allow for different values of the constant. I don't really care because this is just scaling along the y-axis. But it needs to be constant across the entire frequency range of the frequencies of interest, and it has to have a linear phase. So, and you've heard, I'm sure you've heard that we talk about this system has a. When it's not constant, we talk about how much of a ripple does it have in its magnitude response, and what is the nonlinearity of your phase response. So you want your magnitude response of the system to be constant across the range of frequencies of interest, and you want your phase to be linear phase as a function of frequency. How would if I were to plot this, here's the plot. Here's my f-axis. This is how the magnitude response should look like. So this is magnitude of h of f. It has a constant value across the frequencies of interest, and then and the phase is linear. So let's say this is the phase. So this is the angle of h of f. I keep on saying over the frequencies of interest, right? And you will see why do I say that a little bit later. I can give you a little bit of preview that making a system that has all of these properties across the entire range of frequencies is not possible. But that's not the goal. We always, remember, one of the things that we talk about the signal is the signal bandwidth. And that means what are the ranges of frequencies, or what is the range in frequency domain that the signal occupies. So what I'm going to be requiring for the system to be distortionless is to behave well with respect to the portions of the frequency domain where the signal has significant components. If the signal does not have a component in this particular frequency range, it is irrelevant for the system, how the system behaves there, because the input is 0 to begin with, right? So this is what we call, so let me say, this is a baseband ideal, baseband version of distortionless system. Okay, and the summary baseband version of the distortion system, the magnitude is, amplitude is constant, and the phase is linear. Now, what about if the system is not a baseband? Let's take a look at bandpass system. I use these two terms. Let me make sure you understand them. What is a baseband system? Baseband system is the one that operates around DC. Majority of the signals that we process in let's say, signal processor communication are close to DC. If you look at voice, it's 0 to 4 kilohertz. If you look at music, 0 to 50 kilohertz. Video, 0 to 5 megahertz. But they're all having the frequency ranges down around 0. You know very well that in order to transmit these signals, we usually upconvert them, right? We modulate them and put them somewhere else along the frequency axis. For example, radio signals are in hundreds of megahertz of the carrier frequency. So we take the baseband signal, which is 0 to 15 kilohertz, and we put it on, let's say, 98.5 megahertz carrier frequency, where it occupies 200 kilohertz of the band. This is, for example, WFIT, when we take the speech signal and we broadcast it over the air, but we have to perform the frequency translation. So it is of importance for us to understand, well, how does the ideal distortionless system look like when it is a bandpass system? Do these two conditions that I have here still apply? You will see they don't really apply. Actually, we lock out here, and we have a slightly less of a strict condition, because this is quite strict. You want to be flat across, linear all the way through. But let's see what this becomes in the case of a bandpass system. And what you find out is that H of F, in the case of the baseband system, this is your ideal distortionless system, has to be of the following form. It has to have a still constant magnitude, but the phase, because it has to be G 2 pi, and then I have here phi 0 minus Ft. So what we allow is, we allow that the phase does not have to go through the origin. Here, the only way how you can make a linear phase is to make sure that it goes through origin. Here, the phase does not have to go through origin. So, how does that affect our signal? So let's take a look. Consider a signal z of t, which is equal to x of t times cosine 2 pi f0t. Where is the spectrum of this signal? If x of t is a baseband signal that occupies a portion of the spectrum from 0 to w, then according to the modulation property of the Fourier transform, the spectrum of this signal is translated to the carrier frequency. So it will occupy the portion of the frequency axis f0 minus w to f0 plus w, right? So this is translation, how we translate the spectrum of the signal in the frequency domain. So what I was saying is this: h of f is equal to 0 for any f larger than w. This is a band-limited signal occupying just 0 to w in the frequency domain. If I were to draw this, this is the spectrum of h of f minus w plus w. Right? This is how my baseband signal would look like. This case cosine 2 pi f0 t we usually refer to as carrier. Why? Because this sinusoidal is actually modulated by this particular signal, and in the process of modulation, the whole spectrum of this signal is translated to a different range. In other words, z of f is going to be 1/2 x of f plus f0 and plus 1/2 x of f minus f0. So how does this look like? Well, here's your f0. Here's the z of f. Right, it extends from f0 minus w, f0 plus w, and here minus f0 plus w minus f0 minus w. So that's my signal. That's a bandpass signal that I'm going to be processing now with this bandpass system. So let's take a look at what happens. Y of f, as you know, is going to be equal to z of f times h of f. I'm looking what the frequency domain, if I present my signal, which is this guy, or this is the Fourier transform of it, to this linear system. This is what the frequency response of the, or Fourier transform of the output would look like. Now, substituting the values here, you have that this is G0 over 2 from this guy here. Then we have x of f plus f0 e to the j 2 pi minus f0 minus f dg. And then I have plus x of f minus f0 e to the j 2 pi pi 0 minus f dg. Okay, that's a product of these two. So now if I take the y of t, which is an inverse Fourier transform of y of f, I end up with just a little bit of work, but let's just do it. F minus 1 of this whole thing goes downstairs. So this is f of f plus f0. I forgot G0 over 2. G0 over 2. And then this whole thing, x of f plus f0 e to the j pi minus pi 0 plus f, minus f t g plus x of f minus f0 e to the j 2 pi pi 0 minus f. So I need to determine the inverse Fourier transform of this guy. The way I'm going to split this into two integrals, so this becomes G0 over 2, integral when f goes from minus infinity to plus infinity, x of f plus f0 e to the j 2 pi minus pi 0 minus f dg e to the j 2 pi ft df. That's the first integral, right? Just this operator going through the first portion of this parenthesis here. This is essentially taking the inverse Fourier transform of this section here. And then there's another, the second integral, which is g0 over 2, integral when f goes from minus infinity plus infinity, x of f minus f0, e to the j 2 pi by 0 minus f dg, e to the j 2 pi ft df. Right, taking the inverse Fourier transform of the second part. All right, so let me continue over here. It gets a little bit messy, but you know, when the smoke clears, you will see that the result is really simple of all of this. So this y of t becomes now, from the first one, I can take the stuff outside that does not depend on f. This is this g0 over 2 and j2 pi minus f0, pi 0, sorry. So this is g0 over 2 e to the minus j2 pi 0. And then what is left is integral when f goes from minus infinity to plus infinity, h of f plus f0 e to the j, now e to the j 2 pi f t minus tg. j 2 pi f t minus tg df. And then the second integral is g0 over 2 e to the j 2 pi 0, integral when f goes from minus infinity to plus infinity, h of f minus f0 e to the minus, well, I can just put the same thing, j 2 pi f t minus tg df. So if I, let me see what this, so if I introduce a substitution here, nu in the first integral, nu is equal to f plus f0, and in the second I introduce the substitution, nu is equal to f minus f0, then this becomes g0 over 2 e to the minus j 2 pi 0. Integral, let's put here, substitution nu is equal to f plus f0, and here the substitution nu is equal to f minus f0. So you end up with nu goes from minus infinity to plus infinity. You can see that nu and f, when f is in minus infinity, nu is in minus infinity. Then you have x of nu e to the j 2 pi nu t minus tg df. And then this was a nu was equal to, f was equal to nu minus f0. So here, I'm going to have an additional term, e to the minus j 2 pi f0 t minus t from the first integral. So you have this part, and you have this part, and you have this. And then the second one, g0 over 2, e to the j 2 pi 0. Nu goes from minus infinity to plus infinity, x of nu, e to the j 2 pi nu t minus tg, sorry, d nu here, d nu. And then here I had f, but f is equal to nu plus f0, So I have an additional term here at the end, e to the j 2 pi f0 t minus tau g. Okay, so all of this is there. So if we now take a Fourier look at what we obtain, this here is an inverse Fourier transform at what time? The time is t minus tg, right? Here, this is the same as the inverse Fourier transform, but just t is equal to t minus tg. And I get the same thing at both places, right? So I have now, this is equal to g0, this guy here. Then I can write this thing for common for both of them, which is x of t minus tg. And then I put 1/2 downstairs. And then I'm left with these two terms, right? Let's write this one first. So this is e to the j 2 pi f0 t minus tg plus phi 0. Oh, this is not f, this is phi. Phi 0. And then here plus e to the minus j 2 pi f0 t minus tg plus rather minus phi 0, right? Okay. So what is this? Cosine, right? So as a result, you can see that I have that this is g0 x of t minus tg, and then I have cosine 2 pi f 0 t minus tg plus some phi 0. Okay, so let me summarize what is it that I get a little bit different signs, but I think it's wrong in the notes. So here's what we're having. Let me sketch this in the frequency domain and then explain what actually happens to the signal. If you look at the frequency domain, here's a let's say portion of spectrum that is occupied by my signal z of f. This is remember, this is my 2w. This is a carrier frequency here, and minus f0. This is 2w where the signal exists. So this is where my signal exists, right? In this portion here, I have a band test signal x of f, x of t. Remember, which is band test signal, which is x of t times some cosine cosine 2 pi f0 t. So this is where my z of f is existing. Now let's take a look at what I claim is a distortionless system. Let's say I have a system that has a frequency response that looks like this. Its magnitude response is constant, right, over the frequencies of interest, right? So these are my frequencies of interest, and the magnitude is constant there. And after that, I don't really care because the signal has no components. So this is my G0, or rather G0 over 2 because I'm drawing double side. The completely linear phase requirement would mean that this goes to 0, but I'm allowing that the phase does not necessarily go through 0. Even the phase that looks somewhat like this is, let me actually make it a little bit more so that you see what I'm talking about. Over this interval here of interest, if I look at what my phase looks like, it is best approximated with this line that that hits this here at minus phi 0. So let's see if I have. Well, people usually try to avoid it, but it becomes complicated. So this is the phase over frequencies of interest. This is the magnitude over frequency of interest. Likewise, here's the phase of the frequencies of interest, magnitude, and here is the phase over frequencies of interest. And this here is minus phi 0, this point here is phi 0. So this system also has, is a distortionless system when it comes to the signal. It has to satisfy the following condition. Its overall frequency response. It has to have a flat magnitude, which it does here. It has to have a linear phase, but up to some angle phi 0. So it is approximately linear, but it's not going through the origin necessarily. And if that happens, I treat this system also as a distortion. But what is the consequence of this not going through 0? Remember, in my baseband system, this went through 0, right? And if I had a system that encompasses these frequencies and has a linear phase throughout, it will be distortionless by the previous case. But this one is a slightly lower requirement, slightly looser requirement, because now all I require is that the phase is a straight line, not necessarily going through the origin, through the band of the frequency of interest. As a consequence of that, I'm getting a signal that is slightly different than what I had originally. Let me point the difference. Here's the difference. I have my input signal was z of t, which was equal to x of t cosine 2 pi f0 t, right? This is my bandpass signal that is input to a linear system. The system has a frequency response h of f, which is equal to g0 e to the j phi 0 minus f dg. As a result of there's some 2 pi here, right? Times 2 pi. Did I put here 2 pi? Yeah. Then my output signal in this case is going to be equal to x of t minus tg. There's going to be g0 up front. Cosine 2 pi f0 t minus tg. So that would have been an ideal distortionless system according to the previous case. But in this case, since I allow this additional flexibility that my phase does not have to go to 0 when I extend the tangential line, then I have an additional phase. And this, in vast majority of cases, does not matter at all, right? Because you have a carrier that is usually this frequency is so high relative to all the baseband frequencies, so that this phase here does not matter much. So, so let me summarize. In the case of the baseband transmission, ideal or distortionless linear system has a frequency response of G0 e to the minus j 2 pi f0 t tg, where this is not f0, just ftg. It has a constant amplitude in the linear phase, and if the input is x of t, the output is y of t, which is equal to g0 x of t minus dg. Right? So this is a baseband transmission. I'm requiring constant magnitude linear phase. I put the signal x of t, I get scaled and delayed version of the original signal. Now, for bandpass transmission, I say that my distortionless system has a frequency response G0 into the minus J 2 pi f tg plus some phi 0. So I'm allowing that it consistently. So it's going to be j 2 pi phi 0 minus f dg. So this system is slightly more general than this guy. It has a phase that has this linear, this additional constant here. And in this case, if I put input signal z of t, which is equal to x of t times cosine 2 pi f0 t, I have a signal now that is translated to frequency of this carrier. Then my output in this case, y of t, is going to be x of t minus tg times cosine 2 pi f0 t minus tg, and then plus some phi. You notice that this case here is a special case of this one. How special it is. How do I get this one from this case from this case? If my phi 0 happens to be 0, then both cases are equivalent, right? I have a phase that does not curve like this, but goes straight all the way through, which is unrealistic in the real systems, but for the sake of analysis, you can see that this is a subclass of this. Now, in majority of the systems that are bandpass systems, we deal with this thing here. And you have to be aware that the transmission of the distortionless transmission in bandpass systems does not preserve the phase of the carrier. The phase of the carrier may change. And in a lot of cases, that's one of the things that we actually task the receiver to do, to estimate this phase of the carrier, because you cannot, the whole thing is delayed, just like in this case, but there's also a phase shift here that is added, so you always have to estimate that when you receive the signal. Okay? Now,
Excuse me, sir.
go ahead.
So can you elaborate why the phase of carrier doesn't matter to that of our signal? Like there is a phase shift in this band pass transmission of F0, phi 0. Why it doesn't matter, like whatever is the phi 0, it doesn't matter with our actual signal, that is the band transmission?
The simple answer is, what is it's not that it doesn't matter. We allowed it and we still call this distortionless transmission. Remember, our first definition of the distortionless transmission is that the output needs to be like this. Right? And if I extend this to this case, that means this should be the output. Right? Instead of t, put t minus tg. And this is in a strict definition. When you try to use this in practice, you never get them, right? Because you cannot really make the filters or systems that act like bandpass filters that have the linear phase that goes to origin all the time. So then what we do is we think about it this way. If I look at this z of t, I can distinguish two components, x of t and this cosine. X of t is really what the signal is, right? This cosine here is a carrier. Its purpose is to translate this signal to the frequency, where I want it to be, right? So now, if I receive something that is like this, is the signal actually distorted? According to the first definition, it is. But according to what this is used for, you say, well, what has happened is I preserved my entire signal that I care about. It's delayed, which I allow, and it's scaled. There is G0 here, so it's scaled potentially. But what has happened, the carrier changed its phase. Well, in majority applications, the next step in your processing is you get rid of this anyway, right? You bring everything to the baseband, and you care about only this portion of the signal. So, the fact that the carrier changes phase ultimately does not cause any distortion in your signal, right? But think about it, this is a voice, right? Transmitted over radio waves. You take your voice, you send it over, and this is what you get. Now, the fact that the carrier changes phase, you don't care. All you need to do is actually deal with it and make sure you estimate the carrier phase and then bring everything to the baseband correctly. But you wouldn't say that this is a distorted signal because you're going to be extracting this, and this is not distorted at all.
So but that is being embedded in our carrier signal, right? Our
Yeah.
actual frequency signal is being embedded in carrier signal, and if there is a phase shift, then won't there be like stretching or shifting of the original one?
No. This is a linear, just the translation in the spectrum. This is addition to the phase, right? You can clean this up easily. As a matter of fact, you cannot, most receivers don't count on knowing the phase. So this is something that, that you take care of with the receiver. Right? The thing is, this signal here that you care about is coming undistorted. And if you look at just this piece, they are the same, right?
Yes.
Yes.
Yeah, so that's the piece I care about. I allow this flexibility. If this is kind of post-analysis, right? If I can make it this way, I would probably say this is it. But in general, you cannot make the phase behave this way over large variety of frequencies. So then you say something like this, okay, what I want to have is over the frequency range that are of interest. Let's say I'm transmitting at this frequency for this bandwidth. I want to have a flat magnitude and phase that is just a straight line. And I'm not worrying about the straight line going through the zero. It's too much to worry about. Because I know that if it doesn't go through zero, all that it will do is it will actually change the phase in my carrier, which I can clean up as a receiver. And I still call this distortionless transmission. Right? Go ahead.
How do I modulate the output?
How you demodulate the output?
Yeah.
That's a whole different course. It's called communication
Because
theory.
you talked about the phase one, right? Okay.
Yeah, this is called communication theory and also digital communication that 90% of the time just talks about how you modulate and demodulate.
Okay, because the purpose of the band signals, you need to demodulate that and then first to get the output, right?
Yeah, and you're correct, but it's outside the scope of this course, right? Here, what I really wanted to point out with this analysis is I wanted to present to you what is it that we call distortionless transmission. This one is easy to understand, right? But if you try to apply this one to bandpass signals, you end up with a criterion that is too strict. And if you say, I want a distortionless bandpass system that behaves this way, chances are you're not going to be able to make it.
Why you said it's too strict? What is the criteria that's making it
Zero.
strict?
It has to pass from zero. We cannot make it pass from
It's
zero.
the restriction is is this one.
Yeah.
If you introduce this one, you actually end up with a relatively mild condition that can be satisfied in a lot of cases. What you do is, what you find out is this. If you look at, let me just draw the positive frequencies. Let's say this is the frequencies of interest, right? This is your band. And you design a system and let's say it behaves somewhat like this, right? That's its magnitude response. And you look at the phase response, and let's say the phase response is, I guess, let's say somewhat like this, right? So that's the overall system. Let me reduce this, and let's say this is the bandwidth that I'm utilizing. Then what you find out is this is very close to constant here. And this, when you look at this curve over a small range of frequencies, this curve is linear too, right?
But it won't pass
It does
from
not
zero.
go through origin,
Yeah.
right? Well, this one will. This one will, right? Because it's a linear system, and the phase has to be odd function of.
But we are not interested in that. We are
But
interested in
we're interested how it behaves here, and what you find out, if you extend it, it does not pass the origin. Does that present a problem? According to the first criterion, it does. But when you analyze what is the problem, it is really minor nuisance that you can get rid of, So we extend the definition of what we consider as a distortionless system to the one that actually fits this description. And when you talk to people, when they say, okay, I want to have, the overall end-to-end frequency response of this needs to satisfy flat magnitude and linear phase. What I mean by linear phase is over the range of interest. This needs to be approximately straight line. And if it doesn't, then we design equalizers that make that happen. Right?
Sir, one question maybe not related to this. Just suppose we have to pass some information over the signal, and that is neither voice signal or anything that is like audible to human being. And we want to like keep it more noise protected. So we will go on higher frequency range. So is there any criteria so that the actual signal and the modulated signal, the frequency of these two should be like difference of at least minimum of this much or that?
No, because the noise over the entire range of frequencies of interest, the power spectral density of the noise is constant. So as far as the noise is concerned, there is no preference across the frequency axis. You know, so everywhere you work, you're actually working against the same noise. Right? So to answer your question, no. I mean, theoretically speaking, the noise is everywhere the same.
No,
That's
sir,
one of the kind of cool things. Right? There's eventually everything falls down, and the power spectral density of the noise falls down, but it falls down at such a high frequencies that our entire universe of communication actually works in the portion of the noise spectrum over which the noise can be considered as flat.
Okay, so now question B.
Uh,
Okay, I'll ask you later.
Okay. All right. So let's now look at the difference between ideal and practical filters. Now, there is a difference between ideal and a distortionless, right? And there's now a difference between ideal and a practical. And let's highlight these differences. So let's start from the basement. How does the ideal distortionless filter look like? Well, here's the frequency response. The magnitude response is flat from in some range from 0 to W. And the phase is linear. Right, so this is the magnitude of H of F, and this part here is angle of H of F. Analytically, H of F is can be represented as rect of F over 2W e to the minus j 2 pi f d. This rect is the pulse, right? The rectangular pulse that has a width of 2W and it's centered at the origin. Right? So this is this magnitude, and then e to the minus j 2 pi f t. This d is index, the delay time dv, and that's essentially the slope of this curve. If I were now to say, okay, this is the ideal filter, it's distortionless too. Let me try to make this one. And let's see what the impulse response of this guy would be. You would do something like this. H of t is going to be the inverse Fourier transform of H of f. And this is a pulse. So you know that the inverse Fourier transform of the pulse is what? Sync. So you end up with, after some steps, 2W sync of 2 pi w t minus t d. So that's how the impulse response of this filter looks like. If you were to plot this, here's what you find out. This is t. This is your age of t. This is time t0. And this is the impulse response of this filter. What's wrong about this picture? Is this part is wrong. Why is it wrong? Because it says if I hit this system with an impulse at t equals 0, then this system actually responded before I placed the impulse. See what I'm saying? This impulse response exists before t equals 0. How do we call this kind of system? Non-causal. So we get one interesting consequence here, that yes, we were able to define what the distortionless filter looked like. We tried to make it as an ideal filter, and we did the brick wall. You can do it theoretically, but you cannot realize that practically. So every system that we're going to be dealing with will have some level of distortion. So how do we deal with this? Well, this delay here that seemed to be initially to be our enemy, right? To actually say, well, I would like this TD to be the smallest possible, actually end up being our friend. So practical implementation of the filter is actually, if I were to introduce this delay and I increase it, so in practical implementation, we make, this is TD is relatively large. And what that does is this. You look at the time axis, t. Let's say this is your TD. Then your impulse response is essentially this. And you know that this guy goes to infinity, but if you get rid of and truncate everything that is happening here, nothing major changes, right? So if you introduce the delay, you can actually push this impulse response to the point where the fact that all of these things are neglected doesn't matter at all. And that kind of tells us that that we can actually come as close as we want to this characteristic, but at the expense of increasing the processing time. Right? And we do that sometimes. Okay, so let me go back and look at, go back to the power and the energy of the signal. We discussed that at a great length for the Fourier series. We saw that we can calculate the power of the signal either in a time domain or a frequency domain. And the relationship, the time domain is by definition how we calculate power and energy. But in frequency domain, what allows us to do this calculation is something that we call Parseval's theorem. Parseval's theorem was actually of a tremendous value to us. It showed that what parts or what cosines are actually carrying what portion of the signal power. In that case, power, because we're talking about power signal. Now, we learned how to decompose any signal, non-periodic, into sinusoidals again. There's no question about how you calculate the energy of the signal in the time domain. The question that we pose here is, can I calculate the same thing directly from the frequency domain? In other words, is there a version of the Parseval's theorem for non-periodic signals? And it turns out there is, and let's just go and pursue that and derive the expressions. So signal energy. And I don't know if your book calls it this way, but I like calling it Parseval's theorem, because it's essentially the same thing. So consider a periodic signal x of t. The energy of that signal, Ex, is defined as integral when t goes from minus infinity to plus infinity, x of t magnitude squared dt. We know this is a time domain definition of the energy. Nothing changed from our lecture number 1. This is how we define it back there. And this further can be said that this is t goes from minus infinity to plus infinity. Another way to write this, x of t, x complex conjugate of t dt. This allows us, this one here can be, this one explains why there's a need to put the absolute value here. Because both of these are applicable to complex signals. If x of t is real, then x of t is equal to x complex conjugate, and it's just both of these boil down to x squared of t dt. But if x of t is complex, then you have to put the magnitude or calculate it this way. Now, let x of f be a Fourier transform of x of t. What are we trying to do? We're trying to calculate this same energy directly from the Fourier transform of the signal. So x of f is the Fourier transform, and then from there, it obviously follows that x of t is going to be integral from minus infinity to plus infinity, x of f e to the j 2 pi f t df. In other words, I'm saying that if x of f is Fourier transform of x of t is an inverse Fourier transform of x of f. The x of complex conjugate of t is going to be complex conjugate of this, but this is an integral when from minus infinity to plus infinity, x of f complex conjugate e to the minus j 2 pi f t df. Just a complex conjugate of this integral. So now what I'm going to do is take this, put it instead of x of t, take this part, put it instead of x complex conjugate, and then through some steps determine what the energy is directly from x of f and x complex conjugate. So therefore, I have this Ex is equal to integral, and I'm going to be writing what I'm integrating over so that there is no confusion. So first I integrate over t. T goes from minus infinity to plus infinity. X of t, I'm going to write as this. So this is going to be integral. F goes from minus infinity to plus infinity. X of f e to the j 2 pi f t df. So that's my first integral. And the second integral is nu goes from minus infinity to plus infinity. X of nu complex conjugate e to the minus j 2 pi nu t d nu. Right? And then I have to put times dt at the very end to finish this integral. So this part is x of t. This part is x complex conjugate of t. I put nu so that I don't have two f's, right? F would be dummy variable, and so now, just like in many of the proofs of this nature, the next step is to change the orders of integration. So let's first integrate with respect to f and nu, and then group everything that is t at the very end. So we have integral when f goes from minus infinity to plus infinity. And then integral when nu goes from minus infinity to plus infinity, x of f times x complex conjugate of nu. And then I have integral when t goes from minus infinity to plus infinity. And I can write here e to the j 2 pi f minus nu t dt. Or, yeah. So now, this seems a little bit, and then I have to put D, U, and DF at the very end. Now, this looks a little bit daunting because this looks like an integral that you go over two coordinates, right? Like it's a surface integral, two-dimensional. But this would have been the case except for this. Look at this as a let's say inverse Fourier transform. What is it an inverse Fourier transform of? I can put here 1, right?
Delta.
Right? So, or I can say this is, just for the sake of, let me put this nu minus f, and then put the minus here. Okay? So this is a Fourier transform of 1. So what is the Fourier transform of 1, of a constant? It's a delta. At where? At the f, right? But you see here, instead of f, I have nu minus f. So this whole integral here amounts to delta of nu minus f, right? So now, I am integrating over, let me just draw that. Let's say this is an f coordinate, and this is a nu coordinate. And this integral here says d nu df, so that means integrate over entire plane. But then this delta says, wait a minute, everywhere where nu is different than f, this is equal to 0, right? The subintegral function is equal to 0. So this double integral here collapses into, so I'm actually integrating only over this line where nu is equal to f, and not over the entire area. So this monster triple integral actually becomes very, very simple. So this EX becomes an integral. Let me just write it a little bit more detail. Minus infinity to plus infinity. Integral nu goes from minus infinity to plus infinity. X of f, x complex conjugate of nu, delta nu minus f, d nu df. And as I said, this is double integral, but it's really a f goes from minus infinity to plus infinity, x of f. Only nu has to be equal to f, so this becomes x complex conjugate of f df. And this simplifies tremendously as f goes from minus infinity to plus infinity, h of f magnitude squared df. So we get a really cool relationship that energy of the signal, I can say energy of the signal x is integral when t goes from minus infinity to plus infinity, x of t squared dt. Or I can say integral when f goes from minus infinity to plus infinity, h of f squared df. Right? So I can calculate the energy either in a time or a frequency domain, and in both domains, it is the area under the curve of the magnitude squared of whatever is that represents the signal in that domain. If I have x of t, I take the magnitude squared and take the area under the curve, that's the energy. And if I'm looking the same thing in a frequency domain, then I square the Fourier transform of the signal, and then I take the energy under the curve, and that becomes the energy, the area under the curve, and that becomes the energy of the signal. All right, so I will have to stop here because we're over the limit. Then make sure you study over the weekend. Let me assign some problems, and then we'll have a review next Tuesday in preparation for the test. So problems are these. 731, 732, 733, 734, 735, 738, 739, and 731. Okay? All right, thank you so much. Sorry about the delay at the beginning.